Okay, welcome to lecture 22 of CSE 548, the analysis of algorithms. We just passed back the midterms, so you don't get to see the sorting this time. But let's go through first what the scores were on the midterm, then we'll go through the answers. Okay, so it's some idea as to what's happening. For the undergrads, this is the undergraduate distribution. Okay, the high on the undergraduates was a 93. Okay. The low on the undergraduates was a 0 if you didn't take it, and a 31 otherwise. The average on the undergraduates, excluding the zeros, was a 64. Okay, so if you want to see roughly where you sit, you can see what it is. The distribution was fairly flat, okay, on that range between there. So you'll see roughly what that. You can figure out roughly what that means. Okay, yeah.
Would you consider maybe an A or a B?
What I consider. I guess it's a little hard to judge on a basis of on the basis of one exam. My usual sense is, okay, you know, if you got nickeled and dimed within one problem or so of the right answer, okay, that's probably okay. So presumably the A's are somewhere in roughly here. Okay, the B's are presumably somewhere roughly in here. Okay, the C's are roughly somewhere in here, and below that is below that, roughly in there. Okay, I will be posting ranks for the we will be posting ranks hopefully by let's say later today that would have up to the third homework and the first two midterms. So there you can get some better idea cumulatively how you rank. Okay, but again, if you want to see what your final grades are, you'll have to wait for the end of the semester. For the graduate students, the average was a 70, which wasn't too much higher than the undergraduate average, even though they had an extra problem to work on. So presumably the extra problem presumably cost people points, okay, possibly, rather than help them. But the high score was 110, okay, so it was possible to complete the exam and do close. The low score was in the 30s, okay, and again, the average was about a 70, okay, and again, the distribution was fairly flat, okay. For the graduate students, A-ish may be somewhere in here, B-ish may be somewhere in here, okay, and you know we'll see what that means later on, okay. So look at the global scores and see. But you should be able to figure again, getting within one problem of the top one, maybe something in here is probably some flavor of an A, but I don't want to be held to that, okay. Just as a rough idea, okay. Any questions about what the scores roughly mean? Okay. Again, when you average things out across several exams and stuff, little variations go away. Okay, let me go. First of all, any questions about what the grades are, or what they mean? Okay. Let's go through what the answers were on the exam. And if you have any questions, we can talk about them. Okay. The first problem was was intended as sort of a dynamic programming problem. Okay. The problem was that you wanted to find for a given, let's just take a look at this thing. The range from beginning to end, okay, which, if you add up all those numbers in the range, okay, came up to the highest total. Now, the trivial algorithm would be, since every range has to start at a place and has to end at a place, would be you pick for every starting place, for every ending place, sum up the numbers between there. Okay, and that would be an n-cubed algorithm, because n squared, n starting spots, n ending spots, potentially n numbers between, bop, bop, bop. To get it down to n cubed, which was the first point, the trick to get that to n squared, the trick was to see you wanted to try to make that computation of the sum faster. And one way to do that was to store the running sum. Okay, let S sub I be the running sum of the first I numbers. Okay, and then if you did that, you stored 31 plus 41 plus 51, dot, dot, dot. The sum from here to here is simply going to be the running sum here minus the running sum there. So in constant time, you could compute what that sum actually is. Okay, and that would be n squared times that. Okay. Since more people had got this part than the second part, we ended up making this worth more than the second part. Okay. Okay, so more people got the first part than the second. We gave a little bit more of the weight of the problem to this problem than to the second part. What was the second part? Okay. The second part asks to now give a linear time dynamic programming algorithm for this problem. Okay? And the key idea here, okay, is to define what is the recursive function that you want to know, or what is your recurrence. We let t sub I be the maximum run that ends at position I. Let t sub I be the cost of the maximum run that ends at position I. Okay? So let's think about it. If we now consider what is t sub I, if we know the maximum run that ends at the I minus first position, and we add the ith element to it, if we want to know the maximum value run that ends here, either we're going to use this run, okay, or we're going to declare it to be a 0. So what are sort of the possibilities? Okay? If this was a negative value, there would be no reason why the maximum run would want to include that. Okay? So the maximum run that ends at every position is going to always be 0, at least 0. Okay? Because we're allowed to have an empty run. We said here the empty run totals to 0. So at each position here, if we want the maximum run to end at a particular point, we have the choice: do we want to add, do we want it to be the last element, do we want it to include nothing, or do we want to include something before it? If the maximum value here that ends here is positive, this plus this is going to be the maximum value run that ends here. Okay? By definition, the maximum value, basically the value we're going to get is going to be this plus the value we get from the run to the left of it. Okay? If we already know the maximum value that ends here, our choices are basically we can either take this plus the maximum run there, or if that's all negative, okay, to take a cost of 0. So my claim is to figure out the optimal place to end at each position. If we simply take the max of the optimal place previously plus that, or 0. And now, t sub I will now be the maximum run that ends at every position. What do we know? We want to know that our run is going to end at some position. So let's return what the maximum value of t sub I is over all possible values. This gives us the maximum run that ends at every position. We know the maximum run overall ends at some position. By maximizing over that last sweep, we can find which the best run was. Okay, and this is linear time. Okay, any questions about this particular example? Yes?
Yeah, I didn't quite follow this maximum. Why is it between 0 and...
Well, because what's the definition of the problem? The problem says that you want a continuous run of numbers. You want the maximum is achieved by summing up some group of numbers. When all numbers are positive, the entire array is the answer. That much is clear. If all numbers are negative, the empty array would maximize it. So you're allowed to count an empty array as being 0. You're summing up no numbers, that adds up to 0. So the point being that we don't ever want to consider a sum of a run that ends up negative. Okay, because that's going to be, we would be better off saying don't take anything. If all the numbers were negative, we'd be better off taking an empty thing. Okay? So that's why we sort of given the choice. We have the choice at each point of either including previous numbers or not including any numbers. And that's really what the choice is here. Okay? Any questions about that? How many people sort of see it? Okay? How many people don't see it and want another explanation? Okay? What's the idea here? Let's go through that again. Okay? We know that if we have a run, if we consider what is the run ending at a particular spot, it's going to be some chain of numbers before it. The last number in this run might have been minus 15. Before that, maybe it was 100, and then minus infinity, let's say. Let's say the numbers were minus infinity, 100, minus 15. What is the largest run that ends at this spot? Well, it's going to be the largest run that ends at the previous spot. We have a choice now. Either we're going to use this number or we're not going to use this number. This number is minus 15, which might not seem like a promising number to use, except that we know we've got a run that ends right before it with a value of 100. 100 minus 15 is still 85. So we have the choice of finding the longest run that ends here, plus minus 15, or we have the choice of simply starting and stopping here and retorting a value of 0. Okay, yeah?
What if I have the next number 20, for example?
20, okay, yeah.
Then
Then does that affect the value of the largest run that ends here?
no.
Okay. Does it matter if we have 1,000,000 here? It doesn't affect what the largest run that ends here. Anything you do to the right of this line can't affect the largest value that ends here. Okay? Correct? Because end means stops. We mean left to right end. Okay? Does that answer your objection, or do you have another objection?
It doesn't affect the maximum.
It doesn't affect the maximum that ends at that point.
No, it doesn't. But
How do we know which is the globally best? We know that the globally best has to end someplace. Okay, if this is the globally best, maybe the globally best one ends here. Which is why we need a second step. That once we know the best one that ends at each position, we know that the optimal run ends at some position. We know what the cost of the best run that ends at each position is. We now want to find what is the best run overall. And that's why we now scan over all the numbers, saying, well, what was the best run that ended at the first position, the second, the third, the fourth, the fifth, and took the largest one of those. Okay? Once we have the optimal ending position, we know that the right answer is the longest run, the heaviest weight run that ended at that position. Okay? And this is where we would find the actual optimal. Okay? Does that answer questions, or are there any more questions? I don't mind going through this again, because it's obviously, people, the more dynamic programming you see, the better off you are. Yes?
You have the whole block and then the last element.
Right.
You don't. Oh, I see. That's just the I minus 1. Okay, forget it.
Right. So the trick here is to see that the last decision about what the best run that ends at a particular spot is purely a function of this last item, okay, and the best run that ends at that spot. Because we have to decide either are we going to take this number alone, okay, are we going to sum it, take it plus the best run here, since that best run is always at least 0, it can't hurt to always take the sum of them, okay, once we decide to use this number. Or we may decide not to bother with any of the numbers there, in which case we say the best run ending here is 0, because every run above it is negative. Okay? So that's sort of the idea. Again, once you see it, okay, it's actually not that bad. Until you don't see it, it's confusing. Yes?
For this particular example, 100 minus 15, 20, what will be the value of...
Okay, that's a good... Let's run it on the example of 100 minus 15, 20. Okay? What is the best run, the most expensive run, that ends at this first position? We have a choice of, we know that there's a 0, we can achieve a 0. No, it ends after this number. Sorry, that's a good idea. What's the number that ends, the value of the best run that ends after 100? We have a choice of, basically, either including 100 or not including 100. Which is better, 100 or 0? 100. What's our choice here? We have a choice at this point. Either we can include nothing, which would be 0, or we can include minus 15 plus the cost of the best run ending here. Because if we have a run ending here, we can pair it up with this next element. So what's the cost of the run ending here plus that element, 85. Which is better, 85 or 0? 85. So we can achieve a run of 85 ending here. Why? By going all the way back and grabbing this. Correct? Okay. What is the best run ending here? We have a choice of grabbing a run of 20, okay, plus 85. We can get a run of 105, or we could sort of delete nothing and have it end here without anything. Which is better, 105 or nothing? 105. Which is the best run we can pick up overall? 0, 100, 85, 105. This one. So the best run we get is 105, which happens to be the whole thing. If, on the other hand, this number was 10, this would be 95, and the best run overall would be just that. Okay? Any questions? Yes?
So one has to do some kind of a second linear path.
So one has to make a second linear pass overall to get what you really want. Okay? You want to compute what basically the first step is computing what you need to get the answer. The second is where you compute what you really want. And again, we've done that before. If you remember back to the Bytonic tour example. Your recurrence of what you were computing was storing partial paths that later on you were going to go build the best thing from, the best cycle from. Okay? Any questions about that? Yeah?
What if we had a negative value before the 100?
What if you had a negative value of before 100? Let's say that we had, how negative you want it to be? Let's say minus 1. Innocently negative number. Okay? What's the best tour that ends at this point? Minus 1 or 0? So what's going to change? Nothing has changed. Okay? Because our best choice here was between a minus 1 or a 0. We would have grabbed the 0. Our value that we have here is still the same.
But then wouldn't the tour that ends after 100 be 99?
No. I still can grab this. My goal is to find the best possible subrange. This subrange, I can still get my subrange from here to here, totaling up to 105. Okay? You want the problem asks for the longest contiguous vector, okay, of 0 or more elements. Okay? Does that?
I understand that, but if you're saying that TI, we either say it's 0 or
Right.
add it to what we had previously.
So what is the longest run ending after, what is the cheapest, the maximum cost run ending after the first element? 0. What's the maximum cost run ending after the second element? We have a choice of 100 plus 0 or 0. So we grabbed 100. So we know that the best run has to end after some element. We sweep through, we know the best run ending at each element, pick the optimum of those. Okay, any questions? Again, these to a certain extent you have to see. Okay? Okay, and I realize that, sometimes you can get stumped getting on them, but this is sort of the idea. And of course, once it's done, it looks deceptively easy, but I realize that. Any other questions about that example? Okay. Second problem was intended, to be an easy one, although some people seem to have had some problems, had some misinterpretations with things. The problem asks, is the path between vertices in a minimum spanning tree necessarily the shortest path between the two vertices in the full graph? The answer is no. Suppose we have an unweighted graph that happens to be a cycle. Okay? Here's a minimum spanning tree. Okay, or maybe let's even make this of weight 2, just to make it a little more obvious that this is the minimum spanning tree. What's the shortest path from here to here? Okay, in the full graph? 2. Okay? So, in fact, that shortest path has nothing to do with the minimum spanning tree. Okay? And there's no connection between them. Okay? So the answer to this is it's not necessarily true that a path between vertices in the minimum spanning tree is in fact the shortest path between the vertices in the graph. The second problem says, now what if the weights have to all be distinct? Okay, is that necessarily make it true or not? And again, if we consider a cycle where, let's say, this edge has weight 1, 2, 3, 4, 5, 6, 7, 8, 9, and the last one has weight 10, all these edges are distinct in weight. The shortest path from here to here in the full graph would still be across the edge we delete, okay, while the minimum spanning tree would be that. So for both of these, it's no, okay? And in fact, many people's example for here would also suffice to show that. Okay? Any questions about that one? The next one asks about bridges in graph. A bridge was an edge whose removal will disconnect the graph. Can a bridge edge be in fact a back edge in the depth first search? The answer is no, because if we consider a depth first search, what's happening? We suddenly have some kind of a back edge. What do we now know? That back edge is going to create a cycle with 3 edges. If you have a cycle in a graph and you blow away one of the edges, can that suddenly disconnect the graph? No, because there's an alternate way to go around it. Okay? So a bridge cannot be a back edge. A bridge has to be a tree edge. Okay? Any questions? Can it be a forward edge? The answer is no, because we've got an undirected graph. There are no such things as forward edges. Okay? Any other questions? Okay. The third one, okay, was a problem on you have an arithmetic expression given as a DAG. Okay? How do you evaluate it in linear time? Okay? Now this is one where there's a lot of I graded this one, okay? Now, the basic idea is to use depth first search in some flavor or another, okay? So anyone who made some vague reference to depth first search got a very substantial percentage of the credit. Now, in order to do this precisely, okay, in order to do this in the proper efficiency, there's some subtleties. And it demanded people to get more credit than that to demonstrate some of these subtleties, okay? What is the problem, okay? Some people suggested that you could start from the root, evaluate the left side, evaluate the right side, and then do the operation of the root between them. So it gave a nice recursive algorithm to evaluate the tree. Now, what is the problem with that? Okay, if you did something that just went like eval left, eval right, and then return left, up, right. What's the problem with that?
On the example, in the middle, the multiplication will be
doing too much work. Because you come out to this point in the tree, you evaluate that, you evaluate that. Here you get here, you evaluate this. If you just have a recursive procedure to evaluate it, you're evaluating this thing twice. Okay? And potentially, in fact, your algorithm could take exponential time on a sufficiently nested example. Okay? If you don't provide some kind of a roadblock to prevent you from evaluating. Okay? So that is one potential problem. Okay? What is another potential problem? Some people suggested, well, we'll do a depth first search, and some people said, well, instead of evaluating this thing, some people wanted to print the statement. Printing the statement could be much more time consuming than evaluating it. Why is that? Because each time you go through here, if you're making a copy of this thing, you're going to be copying. He's going to keep getting substituted again and again and again and again. Okay? And so the length of your formula might be substantially longer than linear. Okay? Notice that, for example, here when we print the thing, 3/4 is occurring twice. By simply repeating more and more edges to nodes, you can keep getting things repeated, and the length of the formula could grow, I believe, quadratically in the number of nodes. So anything couldn't be linear. Okay? What could be linear? The important thing here is that you have to make sure that you store the value of what you have at each node as soon as you get it. Okay? And if you store the values of what as soon as you get it, in such a way that this node knows not to evaluate it again, then that will sort of solve the problem, okay, of the repetitions. Okay? Now, some people wrote complicated and ugly depth first statements in there. Okay? Those got partial credit, but not full credit. Okay? Some people, if they wrote a depth first search and acknowledged what the problem was, that was a full credit. For this one here, my way of doing it was sort of simpler. Okay? What I would do is let v sub I be the value of each node. Okay? So each leaf gets a value that it's assigned. Otherwise, we'll leave them undefined for now. What I did was top the DAG. What did that mean? All the nodes that had dependencies were to the left of everything they depended upon. That meant that now that I had an ordering of the vertices, every vertex from right to left had all of its dependencies taken care of. And now I could simply walk over my topological sorted as the vertices, confident that each operator had both of its values already done. Okay. 2, 3, 4, 5, star, slash, plus, plus. Once I had the topological sort, I could evaluate these things. And for each operation here, I'd know that my values were ready. Okay? And so I didn't have to muss or fuss and wait for things and stuff like that, like certain people's solutions had to do. Okay? And then after I'd done this, I simply returned the root value. Okay? So again, there's subtleties. I wanted full credit. People had to sort of identify what the subtleties is. This is a tree, and this is a DAG and not a tree. And the same thing doesn't go for both of them. Okay? Any questions? Okay? So realize that's why you didn't get full credit if you didn't get the full credit. Okay? Any questions? Problem 4 asked, how do you find the, basically it was about finding all simple paths between two nodes in a graph. The first problem said, prove that any algorithm for reporting all the paths has exponential running time. Well, how do you show that? Well, you'll say, look, if I give you a graph, let's say a complete graph, if you want to know all the paths from S to T in a complete graph, any permutation of the except for the start and stop, is a possible path. Okay? In fact, it's a path, that's a path of length n. In fact, there are other paths that you could use. But if you're printing out all possible paths on a complete graph, you're going to have at least n over n minus 2 factorial, which is exponential. Okay? And so there's no way that any algorithm could print all the paths, an exponential number of paths, print something in polynomial time. So that's really basically what we wanted to see here. For the next problem, basically I wanted to see some evidence of backtracking. Okay? So if you gave some evidence that you were using backtracking, you got the vast majority of the points. Okay? At least 2/3. Okay? And then, sort of based on sort of the plausibleness of your data structures and things like that, I decided whether or not to give the extra points. Okay? But there's two different approaches to doing the backtrack. Very good, because it's actually tricky to do right. Okay? Would have been to generate all permutations. Okay? And then filter out those that were not really paths. That's not so good because it's very easy to get caught into duplicates and things like that. You might print each path more than once. Okay? That's quite likely what would happen. Okay? The second, much better option would be that you simply build a partial solution tree. Okay? That you basically, from each vertex, you do a search and send all possible edges that you haven't used. Okay? You have to make sure you note that you can't visit any vertex you've already visited and grow it from there. So you grow a backtrack tree based on that. Okay, any questions about that? Okay? I was generous on this and on the other one. Okay? Any questions? Okay? The last problem for the grads was intended to be a kind of a hard problem. All the grads getting 120. But probably it seems to have been maybe too hard. The test may have been a little too long to accommodate this. What was the problem? The problem was that you were given a table, you're given a string of symbols, you're given a multiplication table, okay, which is not commutative or associative, okay, and the goal is to find a way to parenthesize the strings so that you get, basically you want to get a desired answer, okay. The question now is how do you go back? It's sort of like reverse engineering. You know that you want the answer to this product to be an A. How do you go back and write the parentheses in to get it to do what you want? So what was the way to do this? Okay, so what's the problem? Now you're given a string, you're given a multiplication table. The multiplication table is a k by k multiplication table. The string has n characters. How do you do it? Some people base things on trying to sort of mimic the n-cubed matrix multiplication algorithm, but it's a different kind of problem, okay? And the results that you need are a little bit different. How did I do it? I set up a function s sub ijc. What does that mean? S sub ijc is going to be true if there is a way to parenthesize the characters from I to j returning a value of c. Okay? Well, so c is a character here. It could be any character of the alphabet. Okay? This is going to be a start left position, right position, alphabet character. For every possible submatrix in character position, I'm going to record whether or not it's possible to realize that, to take this subrange of things and multiply them to get that answer. It's possible that I can multiply from I to j and get lots of different answers. So just returning s sub ij, see what it's equal to, won't work. I need to have that other parameter. Okay, because each from range from I to j can give me lots of different answers. Okay? So for each character for which it's true, I set that true. For which character for which that can't be realized, I set that false. Okay, any questions about what my function is before I show how to compute it? Okay. That said, how do I compute it? Well, initially, all values s sub ij character are going to be set to false, because I don't know how to do that. Okay. Then maybe I'll have to initialize the special case where, where for each pair ij, okay, where I plus 1, I can look up in the table to initialize the initial conditions. The basis case of the main case of the recurrence is going to look like this. For all possible starting positions, for all possible ending positions, for all possible, characters, I'm going to ask myself, okay, what's this needless to say is not readable. If, in fact, for a given ij, okay, I want to know, is it possible to multiply, okay, from I to j to realize a particular character? Okay, what am I going to do? Well, if I go from I to j, there's going to have to be an outermost multiplication. This multiplication, if I'm going to return a value of c, what I need to know is this. I'm going to need to know for all possible k values as intermediates, okay, and all possible sort of choices of characters, okay, is the result of going from I to k, okay, if, okay, now here I loop through for all possible character choices, okay, if, okay, you can't see the loop. Here we're going through for all possible character choices, okay. What we're going to want to do is to say, if we know that this is character S1, ends in character S1 and S2, if S1 times S2 produces the desired character as output, and we can end in here giving us an S1, and end from here to here giving us an S2, then we can get the desired character. Okay? So the point is that we're going to take over all possible choices for the end character, and all possible choices for the beginning character. Okay, there's the alphabet size here, alphabet size there. For every choice in the middle, we'll see, is there a way to end from here to here in that character position? A way to end from here to here in that character position? And if so, what the product we get from here to here is going to be realizable. Okay, and we then look that up in the table, and that does it. Okay, any questions about that? Okay, this is not a trivial one to see. Okay, but I think if you think about it, we're keeping track of everything that you need to know about. Okay, what's the time of this algorithm? Okay, how many cells are there in the recurrence relation? Well, we've got n choices for a starting spot, n choices for an ending spot, and the k choices for the alphabet size. So there's n squared times k, I think it's actually, wait, okay. Wait, no, n squared times k cells. How much time do we spend to update each cell? Well, there's k possible choices for the position where we put the multiplication. Okay? Then there's there's n possible choices for where we put the middle divisor. K possible choices for how this ends, k possible choices for this ends. It takes k squared n time to evaluate all of them. For every single cell, that gives us an n cubed k cubed algorithm. Okay, I can't say. N cubed k cubed algorithm. Okay, any questions about that? Okay. Yes?
Maybe to find out where the first one could end, the last one. Or basically this multiplication table. Can't you do that linear?
Can't you do what linear? The problem is you want to know for any particular, you need to know for a particular, once you've decided where the outermost multiplication table goes. Here you've got this multiplication. You want to figure out, is there a way you can get an A as an answer? You need to check what are possible answers I can get for this, what are possible answers I can get for that, and then check to see if there's any one from here and one from here, which will give me, when I multiply them, an A.
Well, I had the same algorithm. What just bothered me was if you have to go through the complete multiplication table, and what if the result of whatever here, in this case, A times C is C, and your character you were looking for at the moment was an A or a B? Then you wasted.
Okay, so you're saying that you may be able to do this more efficiently by not checking all possible pairs, by doing some form of pruning or some form of pre-processing. The answer is maybe. I won't say you can't do it. Okay? So you might be able to do it more efficiently, but all I ask for is a polynomial time algorithm, and this is simple and clean.
Yeah.
Okay, well, not that simple, but definitely clean once you see it. Any questions? Okay. So again, it was not an easy test. There were, sort of scores were the average score, okay, was, like I said, for the undergraduates about a 65, the graduate students about a 70. Okay, so think of your things in respect to the average. Okay, okay. If you did very substantially below the average, come by and talk to me. Okay, although you may want to wait till we post the grades, the cumulative ranks, just to see how that goes. Okay, any questions about the scores or about the exam or anything like that? Okay, thanks for that. Okay, that said, I'd like to move into the real material for the remainder of the semester. Okay, this is a quite different topic than we would have covered so far. For the most part, so far this semester, we've been looking at trying to design efficient algorithms. Okay, we looked at sorting and searching kinds of algorithms, found efficient algorithms. We looked at graph algorithms for shortest paths, found efficient algorithms. Okay, sometimes we can't find efficient algorithms. Okay, now many of you will go into industry. Many of you will be given jobs where they say, look, here's a problem we need to solve. Give us an efficient program for doing it. Okay? And after you think about the problem for a while, you may not find an efficient algorithm. Okay? There are a couple things you can do at that point. Now you have a problem, you have to solve it. The boss demands to know that that you solved it. What if you can't find an efficient algorithm? One thing you can do, okay, is you can go to the boss and say, I can't find an efficient algorithm because I'm too dumb. Okay? That would be a bad thing to do. Why is that? Because the boss will be unhappy. Okay? And your position in the company will be severely threatened. Okay? So write your resume. Okay? What would be another thing? You work on a problem. Okay? You try to find a algorithm for solving the problem. Okay? You can't find an efficient algorithm. Something better than just admitting defeat would be to prove a lower bound. Saying, I can't find the polynomial time algorithm for this problem because no such algorithm is possible. Okay? If you can prove to the boss that the job they gave you was impossible, any reasonable boss will say that's a good excuse. Okay? The trouble is, it's very, very hard to prove lower bounds. Okay? What does a lower bound on an algorithm's running time mean? It means that, if you could, like we looked at it for sorting, we said there is no possible algorithm using comparisons that will sort in better than n log n time. That we proved. That was not that complicated a proof. What I can tell you, though, is that there's very few other problems for which interesting lower bounds are known. So if the boss comes to you and says, give me a sorting algorithm that runs always in linear time, you can give him the lower bound proof and the boss will go away. But for most problems, it's extremely hard to prove a rigorous lower bound, showing that no such algorithm is possible. Okay? Think about it. You're trying to prove that something doesn't exist. Okay? It makes sense that that's a hard thing to do. So you probably won't be able to prove a lower bound. What I'd like to do is give you something almost as good. I'd like to give you a way to go to your boss and saying, yes, I could not find an efficient algorithm for this problem, but that guy Skiena couldn't do it either. Okay? Even people who are smarter than Skiena. Richard Karp couldn't do it. Robert Tarjan couldn't do it. Okay? Don Knuth couldn't do it. You would like to be able to come up with a way of saying there is no person in the world that could find this efficient algorithm for this problem. Why would you like to do that? Well, that convinces the boss that he shouldn't hire anybody else. Doesn't do you any good to fire you if you can prove that nobody else can do it. So what's interesting about the theory of NP-completeness is that it gives you a way to prove that no efficient algorithm is known for a problem. Okay? And this is kind of an amazing thing, too. Normally, how would you think of proving that no algorithm is known for a problem? Okay? I mean, what would be the way that you would convince yourself that nothing's known? Yeah.
Well, ask everybody.
You ask everybody. Okay? Hey, Skiena, do you know an efficient algorithm? You go to the library. Look in all the computer science books. Okay? But maybe you missed something because maybe it was written in a different language or something like that. Or maybe the book was stolen from the library, okay, with it in it. The amazing thing with the theory of NP-completeness is that we can come up with a rigorous proof, okay, that no algorithm is known for solving this problem. Okay? And in fact, a rigorous proof that there is almost certainly no algorithm possible for solving that problem efficiently. Okay? The exact technical distinction there, maybe we'll talk about a little bit later. But the real idea here is what we're trying to do. We're trying to show that, in some sense, our problem is the same as a problem that somebody famous has looked at, okay, and failed to solve. Okay? And that's what we're going to sit down and try to prove. Okay? Any questions about what the distinction between these three cartoons are? Okay? So what's the idea here? Okay? The historical fact is this, that again, several times we've seen problems for which I've claimed there is no algorithm, no efficient algorithm known. The traveling salesman problem is one such problem. I said there's no algorithm that always returns the correct solution efficiently, in polynomial time. Okay? We looked at the bandwidth problem. I said there was no efficient algorithm known to solve the bandwidth problem. Okay? And again, we had a room full of people here. Nobody could find an algorithm, okay, to solve bandwidth, okay, efficiently, okay, in polynomial time. In the early 1970s, there were literally hundreds of problems that people were interested in computer science. Set cover, traveling salesman, finding cliques and graphs, things like that, okay, which nobody could find a fast algorithm for, okay, and nobody could prove there was no fast algorithm. Okay, that's sort of the annoying thing. It seems reasonable to me there are problems that don't have fast algorithms. But it'd be nice to be able to state for a fact that there is no such fast way to do it. In fact, that's not known, but what is known is that using the theory of NP-completeness, okay, we can prove that all these problems that we're stuck in this limbo of not having a fast algorithm and not knowing for sure that one doesn't exist, okay, we could prove that all these problems were really the same problem at heart. Okay, in the sense that if you found a fast way to solve one of them, you could find a fast way to solve all of them. And if you could find a fast way to solve one of them, if that meant you could solve all of them, that meant that anybody who'd worked on any of the other problems, okay, your fast algorithm would have done something that they couldn't do. Okay? And that's the heart of the claim that I was making before. Okay? If you can find a fast algorithm for an NP-complete problem, that's going to give us a fast algorithm for all of them. That's where the power of this comes in. Okay? Which is really kind of an amazing thing. Okay? Okay? And I actually find this probably some of the more interesting material we'll cover this semester. And so do students in the past have found this. Okay? It's kind of a different way of looking at things. Any questions so far? Okay? What is the problem? The key point when you start implementing algorithms, I think you discovered this when we were looking at the bandwidth problem, is that there is a big difference between time complexities that run in polynomial time and time complexities that run in exponential time. This is the heart of the whole big O notation, is why we defined it really in the first place. If we took a look at a linear time algorithm on a typical speed computer, the time that it would take would grow linearly in the number of elements, okay? And so if you look at it as you double the size, if you go from 10 to 20, you've doubled it, so the time would double. That's what linear time would mean. If you go have an n squared algorithm, if you double the number of elements, you're really going to be squared. It's going to be 2n times 2n. That's going to take 4 times as long. Okay? And if you triple the number of elements, 3 squared, that's going to give you 9 times as much time. If you have a quadratic function, if you take a look at what happens by the time you get to 60, you start noticing a big speed difference. But both of these are still within seconds. Even if we consider a horrible time complexity, like n to the 5th, by the time you look at a problem, what is 60 to the 5th? It's a big number, but if you count, let's say, how many microseconds there are in 60 to the 5th, you're still only to the point where you're talking about minutes by the time you look at a problem of size 60. These are all polynomial functions. The variable is in the lower term, and there's a constant for the exponent. Let's compare this to a function like 2 to the n. 2 to the n is actually faster than n to the 5th when we're talking only about 20 numbers. But remember, each time we go from add one additional element, that's going to double the running time. So by the time you look at a problem of size 60, a 2 to the n algorithm is up to 300 centuries. If we look at a time complexity that runs in 3 to the n time, we're talking about something that's running in 10 to the 13th centuries. There's a very dramatic difference. And remember, n is still very small, only 60. Okay? There is a tremendous difference between the exponential algorithms, even with relatively low constants, compared to polynomial algorithms, okay, which are even with very big constants. So the bottom line is we have a big distinction between exponential and polynomial time. Okay? Most of the time this semester we've only been worrying about going from n cubed to n log n. Okay? But realize that in some sense the bigger problem is going from something exponential to something polynomial. Okay? And when we have a problem that's trapped at these kind of bounds, that means that there's no hope. Okay? That for any large value of n, if there really is nothing better than a 2 to the n algorithm possible for a problem, that means that you can't hope to solve it at all. Exactly. Okay? That's really what it means. Whereas, you know, if you have an n to the 5th problem, well, maybe someone will buy you a faster computer. Buying you a computer that's 100 times faster is going to do you absolutely no good on this. You can tell your boss it'll take you only 3 centuries instead of, actually, no, it'll take you more like 365 centuries instead of 366. Okay? That's not going to make a difference. Okay? So there's a big difference between polynomial and exponential. You've got to feel that. Okay? And what the NP-completeness tools that we're going to give is going to give us a way to separate the polynomial problems from the exponential problems. Okay? It's not going to help us find an n log n solution for an n squared, but it'll let us know that there is nothing better than something that's exponential. Okay, any questions? Still generalities. Okay. The whole idea of NP-completeness, okay, fits on this slide. If you understand this slide, you will understand exactly what we're doing. Okay, so we're going to keep going back to this slide over and over again. Okay? The idea is really actually kind of neat. Suppose I give you an algorithm to solve the Bandersnatch problem. Okay? How many people here are familiar with the Bandersnatch problem? Nobody. Good. It's a name we just made up. There is no Bandersnatch problem. Okay? But it is some problem, okay, that you want to solve. How many people have ever heard of the Bobilli problem? Okay? Again, it's a name we made up. Okay? But suppose I gave you the following algorithm to solve the Bandersnatch problem. Bandersnatch might be TSP, it might be sorting, it might be any kind of real problem. This is just a variable for the name. Okay? The Bandersnatch problem takes as input some data. One way we could hope to solve Bandersnatch would be using what we call a reduction. Translate that instance, the input of the Bandersnatch problem, into a suitable input for what we'll call the Bobilli problem. Maybe this was sorting. Maybe this was traveling salesman. Maybe this was shortest path. Maybe this was approximate string matching. Okay? We translate the input of one into an input of the other. Okay? In such a way that that translation preserves the correctness. What do we mean? Well, think about this basically as a formatting change. We now call a subroutine we have that efficiently solves the Bobilli problem. Okay? Suppose we have one. Suppose you have a Bobilli subroutine sitting around. If you could translate your input from Bandersnatch format to Bobilli format in such a way that the answer to this problem is the same as the answer to that problem, we could solve this problem in the following way. Do the translation, solve the Bobilli problem on the translated instance, and now report the answer to this, okay, as the answer to the whole problem. Okay? If we could always do this translating and this reformatting such that the answer to the original problem is the same as the answer to the output problem, this is going to be a correct algorithm. Why is that? Okay? Because if the answer to this is the same as that, we can report this, and it'll be the answer we give here is the same as the answer to that. So what's the point of this? The key is finding this magical translation. But if we have that translation, what does this algorithm mean? Okay? Suppose this translation took order Pn time. So it took Pn time to take this input and convert it to that. If the Bobilli algorithm runs in order P prime n time, my claim is that we can solve Bandersnatch in time Pn to do the translation plus P prime n to solve the mobility problem. Okay, correct? If this translation did what we wanted, the total time for this algorithm is the time of translation, the time of running mobility, plus the time of reporting the answer. But if this is the same answer as that, it just means we don't have to just print it. It's not a big deal. Okay? So if we have a fast algorithm for mobility, this would give us a fast algorithm for Bandersnatch. Okay? How many people believe that? Okay? But let's look at the other side. Suppose I know that there is no fast algorithm possible to solve Bandersnatch. Okay? Skiena tried it and couldn't do it. Okay, or forget that. Let's say that someone famous tried it and couldn't do it. Okay? Or let's say that we actually had proven that there was no fast way to do it. Suppose we had a rigorous proof that there was no way to compute Bandersnatch faster than P prime n. What does this mean? If we have this algorithm, we know that we could compute the solution to Bandersnatch in the time of doing translation plus the time of running mobility. That's what this algorithm is saying. If we know that there is no way to do this quickly, and we know that the mobility, the translation is quick, what does that tell us about the mobility problem? Okay? We know that to complete the total job is hard. We know that doing the translation is easy. Okay? What do we know about the mobility problem? Okay? It has to be equally hard as the Bandersnatch problem. Why is that? If I swear up and down there's no way you can do it, there's no way you can do it, there's no way you can do it, and you give me a way to do it, that meant I was lying to you. Okay? If there is no way to do this fast, and a fast way to do this would follow from a fast subroutine for mobility, what does that have to mean? There can't be a fast way to solve mobility. Okay? Because it's impossible to solve this quickly. And if you could solve this quickly, you could solve this quickly. Therefore, you can't solve this quickly. And that is the key idea to what we're going to be doing. Okay? That's going to be the idea that we're going to be using to prove problems hard. Okay? If we know a lower bound on how much time it takes to compute Bandersnatch, then we know that the time of doing the translation minus the lower bound has to be a lower bound on mobility. Because if we could do mobility faster than this, we could do Bandersnatch faster than this. And this means we can't do Bandersnatch faster than that. Okay? This is how we prove that you can't do it, given that you can't do Bandersnatch. Okay, any questions about that? Yes?
Why do you subtract the right times?
Well, what are we saying here? I'm saying there's no way you can do Bandersnatch in less than n cubed time, let's say. Suppose I give you a subroutine to run mobility in n time. Does that automatically mean that there's no way that I've proven something impossible? No, because the total cost of doing the Bandersnatch computations this way is the cost of translation plus the cost of solving the thing. Now, maybe the cost of translation is expensive, but the cost of solving this is cheap. So just because I know this problem is hard doesn't necessarily make this hard. It only makes it hard if we know that the translation is easy. Okay? So that says this, that if we know that the total cost of computing Bandersnatch is at least that, the cost of mobility must be at least the cost of the total job minus the cost of the translation. That's why we have that there. Okay? Any question? Question?
The initial thing with the translation, why don't you need to convert the result back into
Well, because of how we did the translation. Okay? We're assuming that the translation we did was called a reduction. What does that mean? We did a special translation such that all the instances of one type, every instance of a G gets transferred to a Y, such that the answer to Bandersnatch of G is exactly the answer to Bobili of Y. If I can do this magical translation where the answer to this is the same as the answer to this, how much work do I have to do to translate the answer back? Nothing. The answers are the same.
Well, if I think about mathematical functions to translate something, it seems like there has to be an inverse function to the translation.
Okay, we're assuming there's a trivial inverse function where you just copy the answer. Okay? So the trick is we're demanding something pretty powerful from this translation. That's the important thing to see here. The whole idea fits on one slide, but it's assuming this very, very powerful translation, this reduction, okay, where we translate one instance to the other such that the answers are exactly the same. Okay? Let's look at an example. Okay? First of all, are there any questions about this? Okay?
Does it
Yes.
also mean that the cardinality of the input set of Bandersnatch and Bobili have to be the same?
It means that you can't change the size of the problem very much. You're right. Okay? That in order to make sure that it runs efficiently here, you can't make this problem much bigger than it was before. So that's a constraint, but we'll worry about that a little later. Okay? Let's look at an example here of a very simple reduction. Well, not very simple, but I think pretty clear and understandable reduction, once you get the hang of it, between two problems you are familiar with, one more so than the other. One problem I've mentioned a couple times this semester is the convex hull problem. What was the convex hull problem? You have a bunch of points, okay, as input. The output is a small polygon that is ordered, where the points on the outside are ordered so as to define a fence that contains all the points, such that this fence is convex, meaning it doesn't go, in and out. Okay? So the convex hull is actually the smallest area polygon, okay, that contains all the points. Okay? And the convex hull problem asks as input, gives you a set of points, and as output asks you, here's point V1, V2, V3, V4, V5, back to V1. This is the convex hull. Okay? Any questions about the convex hull problem? Okay? The important thing to see, which is that every set of points has exactly one convex hull. Okay? And that it's described by giving you this polygon, which is described by ordering the points, ordering some subset of the points. Okay? Any questions about convex hulls? Okay, again, they're useful in a lot of geometric problems and pattern recognition, lots of things. They're good things. Now, I'd like to show you that convex hull and sorting are really similar kinds of problems. What was sorting? Sorting was I give you a set of n numbers. You have to order the numbers from smallest to biggest. Okay? Is there anybody who's unfamiliar with that problem? Okay, hopefully not. That should be a good one. Okay? What I would like to do is to come up with a sorting algorithm that uses convex hull. Okay? Namely, what I'm going to do is, for my sorting algorithm, input to a sorting algorithm is a set of numbers, right? What's the input to a convex hull problem? A set of points. Correct? So if I'm going to translate it, I need to translate each number into a point, right? I'm going to translate each number into a point, call convex hull on this point, and then read off the points in sorted order. Okay? What is my translation? I'm going to give an algorithm to sort in terms of convex hull. How do I do that? Well, first of all, I need to map every point, every input number, to a point. How am I going to do that? One way I can do that is, for each point, each input number x, I'm going to map it to the point x squared. Okay? So what is the number 5 going to be turned into? What point? 5, 25. Okay, that happens to be here. And what is 11 going to get turned into? 11, 121. Right, okay, good. Okay, I forgot for a moment. Okay? So if you give me as input the numbers 17, 13, 5, and 11, in that order, I can take each point, each input, and translate it into a point. Correct? Each point is going to lie on this parabola y equals x squared. Why is that? Because by definition, y is equal to x squared. Okay? What is the convex hull of points on this parabola? Okay, this is the tricky part. Okay, yeah.
Well, the connection of all the points plus one backwards connection.
Right. The convex hull from here to here is going to look like what? Okay. It's going to have an edge that goes from here to here, here to here, here to here, and back. Correct? A property that is neat of the parabola, which maybe isn't completely obvious, but is not hard to prove, is in fact that since the parabola is a convex curve, every single point would be on the convex hull if we chose it. Okay? So any set of points on the convex hull, on a parabola, their convex hull is going to look like that. There's never going to be any inside points. Okay? Because of the fact that it's a parabola. Okay? That you can believe me for if you don't see it. But so what's interesting here? If I give you a convex hull algorithm, how can you use the convex hull algorithm to sort? Okay? You could take every input number here and map it to its appropriate point, 13, 13 squared. Pump this thing into your convex hull program. What's your convex hull program going to return as the answer?
The sequence of vertices.
It's going to return the sequence of vertices, okay, from left to right. Because the point edge from here to here is going to go to its neighbor, and going to go to its neighbor, and go to its neighbor, before doubling back. So what's neat about this? Okay? The following algorithm will sort a set of numbers. Take the set of numbers. For each number, create one of these points on the parabola. Every number will go to exactly one point on the parabola. I will then find the convex hull of these points I created. That convex hull is going to be a polygon where the edges go from left to right points. Pop, 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 pop. Once I have that polygon, what could I do? I could find the leftmost point in that polygon by simply taking a linear scan through them to find what the leftmost one is, and then walk from left to right, reading off the points from left to right. And if on this particular problem, leading up from left to right, I would get 5, 25, 11, 1/3, 21, 13, 113 squared, okay, 17, 17 squared, okay? What would my numbers be in sorted order. Simply ignore all of this, ignore all of that, and spit them out. Okay? Here I'm lying a little bit to what I said to you earlier about inverse transforms, but don't hold me to it. Okay? What I've done here is given you a algorithm which will sort those points using how much time will it take to construct all these points? How much time does it take to take one point and square it? One integer and square it. Constant time is what we usually assume. So to take every point and create every input number and create all the points, that's going to take order n time, correct? Given those points, how are we going to find out which is the leftmost one? Well, that's the one with the lowest x coordinate. That can be done in linear time, correct? Scanning through all the points. Once we have that, since the polygon will have ordered the points, okay, in the desired order, we could now walk through those points in constant time per point and find what the leftmost, then the next leftmost, next leftmost, next leftmost was. My claim is this would take order n time. This would take order n time. And what's really left as to be done is to find the convex hull of these n points. Okay, how many people are with me so far? How many people have any questions? I'm happy to take a question. Okay, but what's the punchline here? This is a perfectly good algorithm to sort. If I give you a proof that sorting takes at least n log n time, remember we proved that earlier. Sorting takes n log n time. What does this algorithm tell you about the convex hull problem? If we know that all of this takes greater than or equal to n log n time, and we could do this in time linear plus the cost of computing convex hull, what does that tell us about the convex hull problem? Can there be a linear time algorithm for finding convex hulls? No. Okay? Why not? If there was a linear time algorithm for convex hulls, what would we do? We could take each point, construct it, order n time, use your linear time algorithm on those n points, order n, strip off the y coordinates, order n. If you give me an order n algorithm for convex hull, you've just given me an order n algorithm to sort. But I proved with the lower bound there is no order n algorithm to sort. So how can you possibly give me an order n algorithm for convex hull? It can't be done. This algorithm and the proof of the sorting lower bound gives us a proof of a lower bound for convex hull. Okay? That's the amazing thing here. Okay? We've used our lower bound on this guy, okay, to prove a lower bound on this guy. Okay? That is the essence of proving things hard. Okay, any questions about that? Okay? So the amazing thing is we've just proven that convex hull must take n log n time. What if, on the other hand, I gave you an n log n algorithm for finding convex hulls? What does this algorithm do? Okay? What good would this algorithm be if I gave you an n log n algorithm for finding convex hulls? What would it give us?
Also a way to sort an n log n.
It gives us a new sorting algorithm. An n log n algorithm for sorting. Why? Because it takes order n, n log n, order n. So an algorithm here gives us an algorithm here. A hardness claim here gives us a hardness claim there. Okay? Yes?
The lower bound for convex hull could be higher, though.
Oh, just by proving this, Just by giving this algorithm, you're right. The lower bound for convex hull could conceivably be higher. I haven't proven to you, I don't give you, just proving this doesn't give me anything as far as an algorithm goes for convex hull. Okay? It gives me an argument you can't do convex hull fast. If you want to say it's even slower than what I have, that may be possible. Okay? In fact, it isn't, but there's no way you could tell from this argument. Okay? Good question. Any other questions? Okay. Start to think about it. Okay? Next class we'll continue on with this. Okay? And we'll start again from that slide of why this thing works. We'll be starting next class with the problem of the day that is the first problem of the day on hardness. Okay, so start taking a look at that chapter. Thanks for your attention. See you then. Bye.